So students, in the first module, there was a section called aircraft refrigeration. So we learned different type of aircraft refrigerations in that section, like a bootstrap, a regenerative, etc. So, but we didn't do any numerical problems on that particular section. So I have asked you some questions in the assignment and internal test and all, but I haven't done any problem in the videos. So someone asked me to solve such kind of problems. He inquired about it. So I'm doing this particular video, a short video, doing only one problem. So this is the problem: a bootstrap cooling system of 10 TR capacity is used in an aeroplane. Okay, the ambient air temperature and pressure are 20 degrees Celsius and 0.85 bar respectively. So the outside temperature and pressure are given. Capacity of the refrigeration is given. The pressure of air increases from 0.85 to 1 bar due to ramming action of air. Okay, the pressure of air discharged from the compressor is 3 bar. The discharge pressure of air from auxiliary compressor is 4 bar, and the isentropic efficiency of each of compressor is 80 percentage, while that uh, turbine is 85%. So this is very important. This concept I think you have learned in the previous class, theory class. So I haven't mentioned this particular thing: isentropic efficiency of compressor and turbine. 50% of the enthalpy of air discharge from the main compressor is removed in the first heat exchanger, and 30% of the enthalpy of air discharge from the auxiliary compressor is removed in the second heat exchanger using rammed air. Assuming ramming action to be isentropic, the required cabin pressure of 0.9 bar. So cabin pressure is given. Temperature of the air leaving the cabin not more than 20 degrees Celsius. So the power required to operate the system, COP of the system. Draw the schematic and temperature entropy diagram. Gamma 1.4, Cp 1 kilogram per kilojoule per kilogram Kelvin. So before that, this is a bootstrap cooling system. So you know how a bootstrap cooling system works. So what is a so ambient temperature enters, a ramming takes place. Ramming takes place isentropically. So there is a pressure increase, and this rammed air goes to main compressor, and this compressor is working using a gas turbine and a combustion chamber. So that part you leave, don't require. And this compressed air comes into a primary heat exchanger, and this heat exchanger through this heat exchanger it rejects heat to the some bypass ram air, and again this will go to a secondary compressor, and its heat will get so its temperature get elevated, and it is again cooled through using some part of ram air through the second heat exchanger, and this cooled air is passed through a cooling turbine and finally to cabin. So this is the process. So there is two compressor, two heat exchanger in a simple bootstrap system. Okay. Now what all things are given uh, total cooling effect. So cooling space and cooling cabin there should be 10 tier of refrigeration, and what the ambient temperature and pressure. So here T1 and P1 are given. T1 and P1 are given. Okay. Then the pressure of air increases from 0.85 to 1 bar due to ramming action. So after ramming, P2 is also given, rammed air. And the pressure of air discharged from the main compressor is 3 bar. So after compression here it will become 3 bar. Okay. The discharge pressure of air from the auxiliary compressor is 4 bar. So here it will become 4 bar, secondary. Okay. And now the isentropic efficiency of both compressor, so primary and secondary is 80%, and turbine is having an isentropic efficiency of 85%. 50% of the enthalpy of air discharged from the compressor is removed in the first heat exchanger. First heat exchanger removes 50% of the enthalpy. Second heat exchanger removes 30% of the enthalpy of air. And required pressure of in cabin pressure is given. So cabin we equal zero point 0.9 bar and some 20 degrees Celsius cooling. So that thing also given. So you need to draw the TS diagram first. So students, this is the TS diagram. So here our ambient temperature and pressure is 0.85 bar, and so this is the first point, ambient point. The air from outside comes. So I will show you in this along with this figure itself. Okay, so here T1 P1 is there. So T1 P1, so this is 0.85 bar corresponding to T1. Okay, from T1 to P1, what is happening? Ramming takes place. So it is rammed to how much? Rammed to around ramming is taking place around 0.85 bar, right? So a 0.85 bar to 1 bar. So this is to this temperature rammed isentropically. So you don't know the temperature. Okay, you don't know the temperature, but you know the pressure, and entropy remains constant. Entropy remains constant. So this is second point. So you know the entropy because it is isentropic process. So you just draw vertically upward. Okay, vertically upward, and then to the compress. Then compression takes place to 3. So if the compression was isentropic, it would have reached the point 3. But since our isentropic efficiency is given, means it is not actually isentropic, it is somewhat adiabatic, irreversible process. So it is getting compressed to 3 dash. The pressure will be same, 3 bar itself. The compressor pressure is given, right? 3 bar. So here efficiency of compressor is given, very important. Efficiency of compressor is 0.85. So what is efficiency of compressor? Efficiency of compressor is nothing but isentropic increase in temperature, increase in T temperature by actual increase in T. Actual increase in T. So what is isentropic increase in T? T3 minus T2 by actual increase in T3 dash minus T2. So this is efficiency, and this value is 0.8. Okay. So this is the important concept. So isentropic increase in T means it is a lower value. So this T isentropic increase is a lower value because T3 minus T2 is less than T3 dash minus T2. So then only this will become less than 1. So lower value by higher value. But in case of, okay, I will explain turbine when turbine comes. Now you understood, right? Now what is happening after from T3 dash to T2? What is happening now? After it is reaching T3 dash, what will happen? It will pass through a heat exchanger. Heat exchanger passing means it is getting cool, in constant pressure. So what will happen? It is cooled to 4. So here it will reach 4. So what is the so here it will, after 4 it will get compressed to 4 bar, right? Isentropically. So actually from 4 to 5 again compression to 4 bar, but since it is irreversible, it is compressed to 5 dash. Okay, again efficiency is 0.85 itself for the secondary compressor also. From 5 from, so it is 5 here. So this is 1 2 3 dash 4. Actually it is 5 dash. After 5 dash to 6 again cooling takes place. So cooling again takes place. So 5 dash to 6 cooling takes place. So this amount of cooling and this amount of cooling, you don't know how much to cool, but it is given that 50 percentage and 30 percentage of enthalpy of air, the stuff from auxiliary compressor is removed. So first here 50 percentage is removed, here 50%, here 30%, then only you can determine the position 4 and 6. Okay, 4 and 6 can be determined only after finding the 50% of the enthalpy getting removed and 30% of the enthalpy getting removed. Then if you reach 6, you will have turbine is isentropic expansion to 7, but since it is not possible, so here the temperature, to what pressure it should be expanded, it should be expanded to, so it is expanding through cabin, so expanding through cooling turbine, and it will reach cabin means 7. So the cabin pressure is given, P7 is given how much, 0.9 bar. So that is why it will get expanded to 0.9 bar. But it is not actually isentropic process, somewhat adiabatic. So it will expand to 7 dash, same pressure but a higher temperature. So T7 dash. So there we have to use a concept called uh, efficiency of turbine. How to calculate efficiency of turbine? So efficiency of turbine is actual decrease in temperature by isentropic decrease. So here actual decrease comes in numerator, because actual decrease is lower than isentropic decrease. So lower by higher. So that should be the idea. So lower is T. Let me rub all these things. So lower is what? T6 minus T7 dash, right? T6 minus T7 dash by T6 minus T7. So it will be equal to 0.85. So this is given. So this much data are given. Now we have to solve the problem. So in order to solve the problem, it is better to find all the salient points. So even though it is not asked to find the different points, so here T1 is given, temperature and pressure are there, but here T2 pressure is only there, T2 temperature is not there, pressure is there. Here also pressure are there, the temperatures are not known. So you have, so try to calculate all the salient points. So T1, T2, T3, T4, T3 dash, T5, T5 dash, T6, T7, T7 dash, etc. All these things you just try to find out. So how to find out all these values? How to find out all these values? So here T7 to T8 is nothing but here the refrigeration effect. The refrigeration effect Q is taking place 7 dash to 7 dash to 8 in the cabin. In the cabin, refrigeration takes place. So final after refrigeration, the air will reach a state called 8. Okay, this you have to remember. The refrigeration effect is given as 10 TR. So 10 TR will be here. 10 TR will be happening here. Okay, 10 TR. Okay, now we will try to solve the problem using our relations for isentropic and adiabatic equations. Okay, how to find out? So this is a bit longer process problem. So first, I will move this figure downwards. So if you have this TS diagram with you, it will be easy to solve. Okay. Now, 1 to 2 is isentropic process, right? Isentropic process or adiabatic process. So, adiabatic process T2 by T1, you can apply this equation T2 by T1 equal to P2 by P1 all raised to gamma minus 1 by gamma, right? P2 by P1. So, P2 is 1 bar, P2 is 1, P1 is 0.85. Gamma is 1.4 minus 1 by 1.4. It will give you a value of 1.47. Okay. Then T1 is known. T1 is equal to how much? T1 is 293 Kelvin. T1, how much it is given? T1 is 20 degrees Celsius. 20 degrees Celsius. So 20 means 293. Therefore, T2 equal to 293 into 1.047. So you will get T2 equal to 306 around 306.8 Kelvin. Okay, well, the T2 is obtained. Now from T2, what is happening? T2 to T3, this isentropic process. Okay, so T3 equal to T2 into P3 by P2 raised to gamma minus 1 by gamma. So T2 is 306.8 into P3 is 3 bar, right? 3 by 1 into 1.4 minus 1.4. So its value will be how much? I think around 420.3 Kelvin. So got T3. Now how to find T3 dash? T3 dash should be found. But you know this equation T3 minus T2 by T3 dash minus T2 equal to zero point 0.8, right? So apply, so use this equation. Here T2 known, T3 known, T2 known. T3 dash is the only unknown. So 0.8 is equal to 420.3 minus 306.8 by T3 dash minus 306.8, and you will get T3 dash as some value around 448.7 Kelvin. So you remember here T3 dash should be greater than T3, okay? Else your calculation is wrong. T3 dash should always be higher than T3. T3 dash should be higher than T3. If you are getting a value lower than T3 means your calculation is wrong somewhere. So that you have to ensure. Now, now what will you do? Now you have got T3. So 1 is over, 2 is over, 3 is over, 3 dash is also over. Now you have to find 4. So how to find 4? So from 3 dash to 4, cooling takes place, right? Cooling is taking place, but it is given 50% of the enthalpy of air discharge from the main compressor is removed in the 50% of enthalpy getting removed. In the question it is given 15 enthalpy is getting removed in the first first heat exchanger 50%. So 3 dash to 4, 50% of heat is getting removed. So how to find T4? So T4, you just do one thing. T4 will be 50 percentage 50 by 100 of T. So this is T4 equal to 50 percentage of, okay, okay, not like that. The 50, enthalpy equal to 50% of the other enthalpy. So enthalpy at, so I will write like this. So enthalpy H at 4 will be half of H at 3 dash. So enthalpy at 4 is Cp into T4. Cp T4 Actually, CP T4 from 270 0 degrees Celsius. So T4 0 degrees Celsius to T4 is equal to half of T3 dash minus 273. So half means 50%, right? 50 percentage or zero point 0.5. T3 dash is how much? So here one CP is there. So CP is 1. CP is there. So CP equal to 1 given. So CP and CP cancel. So don't worry. So T4 minus 273 Kelvin will be equal to half of T3 dash minus 273 Kelvin, and it will be half of T3 dash equal to it will be some around 175. T3 dash minus 273 will be 175. So T4 equal to 273 plus half of 175, it will be some 360.85 Kelvin. So you got T4. Okay. Now from 4 to 5 again, what is happening? So 4 to 5 isentropic compression, and there is an adiabatic compression. Actual compression is adiabatic. Ideal is isentropic. So here you can write T5 by T4 equal to P5 by P4 into gamma minus 1 by gamma. So T5 equal to T4. T4 is 360.85 into P5 is 4, P4 is 3 into 1.4 minus 1 by 1.4, and this value will be 391.5 Kelvin. Okay, 391.5 Kelvin. But efficiency C is equal to T5 minus T4 by T5 dash minus T4, and is equal to 0.8 again, and you will get T5 dash equal T5 T4 all are known. You will get T5 dash as 399 point how much 399 point around 399 Kelvin. So you know T5 is 391.5, T4 is 360. You substitute all this value, you will get T5 dash. Okay, so T5 dash is obtained. So what happened from T5 dash? From T5 dash again cooling to 6, so that will be 30 percentage. 30 percentage decrease, right? So what will be the remaining? So 30 percentage remove means 70% remain. So CP into T6 minus 273 will be equal to 70 percentage remaining, 0.7 into CP into T5 dash minus 273. Okay, so you will get CP cancel, T5 dash is, so you will get T6 as 361.3 Kelvin. 361.3 Kelvin. Okay, 361.3 Kelvin. Now from 7 to 6, what is happening? Sorry, 6 to 7. 6 to 7, isentropic expansion is there, actual expansion is there. So you can use isentropic expansion. T7 by T6 will be isentropic process. So P7 by P6 into gamma minus 1 by gamma. So T7 equal to T6 is 361.3 into P7 is 0.9 bar, P6 is 4 bar. So 1.4 minus 1 by 1.4, and you will get T7 as 0.653. Sorry, not 0.653. T7 has a value around 236 Kelvin. 236 Kelvin. But efficiency of turbine is given like T6 minus T7 dash by T6 minus T7 is equal to 0.85. So T6 is 361.3 minus T7 dash is unknown, 361.3 minus 236 is equal to 0.85, and you will get T7 dash as a bit higher value than T7. It will be 254.8 Kelvin. Okay, so T7 is obtained. So all the values obtained. Now we have to find the power required to operate the system. Before that, to find power we require m dot a, mass of air. Mass of air can be found how? So Q, total tonnage of refrigeration, will be equal to m dot a into Cp into T8 minus T7 dash. Okay, this Cp into T8 minus T7 dash is for 1 kilogram of flow. So if you multiply it with m dot a, you will get the total refrigeration. So total refrigeration is 10 tr. 10 tr. 10 tr is 2100 kilojoule per minute is equal to m dot a into Cp is 1 kilojoule per kilogram into T8 minus T7 dash. So m dot a into T8 is unknown, T7 is 254.8. You solve, you will get m dot a is equal to, so since it is in minute, you will get m dot a in 55 kilogram per minute. So you should be consistent with the unit, since here kilojoule and Cp is also in kilojoule, kilojoule cancels. So this value will be in kilogram per minute. So you got the value of what? Ma. Now power will be equal to work in compressor. Work in both the compressor, right? Okay, work in first compressor is enough. Work in first compressor. Primary compressor work can be found out if m dot a into Cp into T. So here what is primary compressor is happening, work is happening from 3 dash 2 to 3 dash, T3 dash minus T2, T3 dash minus T2. Okay, so if you substitute, it will get 55 into 1 into 448.7 minus 306. So this will be in kilojoule per minute, but we require in kilojoule per second. So divide by 60, so it will become kilojoule per second or kilowatts. So this value will be around 130 kilowatts. So kilojoule per second will be kilowatts. So why kilojoule is coming? Because Cp is in kilojoule per kilogram. Okay. So you got the power. Now COP can be found out using Q by power. Q is 210, 2100, 10, right? 10 tr. 10 tr is equal to 10 into 3.5. 10 into 3.5 kilowatts by power is 130 kilowatts. So your answer will be 0.27. So COP will be 0.27. Okay, so this is how you solve a aircraft refrigeration system problem. So if you understand the concept of the data given in the problem, and if you know which type of system is this, bootstrap or regenerative or intercooling, all these things, you can draw the schematic figure, and then you can draw the TS diagram. If you are able to draw the TS diagram, you will be able to solve the problem. So understanding the TS diagram and for finding these properties at salient points at each position, then you will be able to solve this problem very easily. So that is the concept. Hope you have understood how to solve this kind of problem. Try to solve different problems from the textbook, then it will be easier for you to solve in the examinations. Thank you.